Welcome to the Explainer. Today we're doing something really crucial. We are bridging that massive gap between textbook maritime theory and the high-stakes, purely operational reality of the gas carrier fleet. We're moving way beyond just memorizing regulations. We're going to truly understand the incredibly volatile science of what you're actually carrying out there. If you work on these ships, or honestly, even if you're just fascinated by extreme engineering, getting the chemistry wrong, that is simply not an option. Okay, let's jump right in.
Picture this. You've got three ships sitting side by side at a dock. They look somewhat similar, and people loosely refer to their cargo with the exact same word, gas. But assuming these cargoes behave the same way, well, that is one of the absolute most dangerous baseline assumptions you can make in this industry. Treating all liquefied gas as just this single, uniform category is basically an invitation to disaster.
So here is our cargo hazard map for today. We'll be covering 1. The illusion of gas, 2. LPG, the flexible blend, 3. LNG, the cryogenic extremist, 4. NGL, the unpredictable mix, 5. Lethal chemical gases, and finally, number 6, the 2.8 bar rule.
Section 1. The illusion of gas. A dangerous assumption.
Getting a cargo mixed up on a loading plan is absolutely not something you can just fix with an eraser. A paperwork error on a gas carrier is actually a catastrophic hardware mismatch. I mean, think about it. Pumping the wrong cargo into a tank means you are suddenly dealing with raw physics and thermodynamics that your physical hardware was simply never built to contain. It's not an administrative oops, it is an immediate, full-blown structural crisis.
Section 2. LPG, the flexible blend with propane and butane options.
So LPG is essentially your baseline cargo. It's likely the most common one you're going to handle early in your career, mainly because the ship types are so highly standardized. It's basically a propane and butane mix. Now, because propane boils at minus 42 degrees Celsius and butane boils a lot warmer, closer to minus 0.5 degrees, operators actually have a ton of flexibility. Depending on your exact mix and the voyage, LPG carriers are built to run either fully refrigerated, semi-refrigerated, or fully pressurized. So the key takeaway here, LPG gives you options.
Section 3. LNG, the cryogenic extremist, zero flexibility, methane.
Now, those flexible options we just talked about, they vanish entirely when we shift over to LNG. Minus 162 degrees Celsius. I really want that number to land hard. LNG, or liquefied natural gas, is almost pure methane, and it is a completely different animal. Because of this incredibly deep cryogenic boiling point, there is literally no practical amount of pressure that lets you carry methane warmer than that in liquid form. Above minus 82.6 degrees, methane simply cannot exist as a liquid, no matter how hard you squeeze it. So you have no choice. You must use full refrigeration at atmospheric pressure.
And that is the core concept to hold on to here. Let's compare them. LPG gives you options, refrigerated or pressurized. LNG gives you exactly one option, deep cryogenic refrigeration, full stop. The industry didn't just decide to engineer around cryogenics for LNG, they had to engineer specifically for it because physics leaves absolutely no other choice. Just look at the massive thermal gap between a propane-butane mix and pure methane. We are talking about a difference of well over 100 degrees Celsius. Putting it into perspective like that really reinforces exactly why LPG and LNG require entirely different containment systems, different grades of steel, and honestly, a completely different operational mindset.
Section 4. NGL, the unpredictable mix, variable by field.
NGL is kind of the wild card of the petroleum family, and it absolutely destroys the comfort of a set routine. Why? Well, because NGL isn't just one substance. It's a highly variable, mixed bag of ethane, propane, butane, and heavier condensates that gets stripped out of raw natural gas before it's sent to pipelines. Its composition changes depending on the exact field it came from, which means the boiling range and required tank pressure shift wildly. That variability is exactly why every single NGL load requires its own specific cargo compatibility and containment check. You literally cannot assume last voyage's settings will apply to this one. Every single load needs a complete re-verification. No shortcuts.
All right, let's break the rhythm here for a quick, rapid-fire check. Out of the petroleum family cargoes we just went over, which one gives you absolutely zero flexibility on how you carry it? If you said LNG, you hit the nail right on the head. Methane's strict temperature demands make it the ultimate cryogenic extremist.
Section 5. Lethal chemical gases, toxic and reactive.
Now, petroleum gases are mostly a fire and cold burn hazard. But as we cross the threshold into chemical gases, the stakes escalate wildly. Why? Because these chemicals actively fight the ship itself. A leak here isn't just a fire risk, it is a deadly toxic exposure risk. Take ammonia, for example. It doesn't just poison you, it aggressively eats away at copper and brass. A copper fitting accidentally left in an ammonia line isn't just a simple mistake. It's a slow leak waiting to kill someone. Or how about chlorine? Sure, it's fine on steel when it's perfectly dry. But the very instant it touches a single drop of moisture, it turns into highly corrosive hydrochloric acid. And then we have things like VCM and ethylene oxide. These can actually react with themselves in a completely uncontrolled chain reaction called polymerization, releasing immense amounts of heat. That is exactly why you never ever sail past an inhibitor's expiry date.
Section 6. The 2.8 bar rule, the IMO threshold. So, with all of these incredibly diverse, super dangerous cargoes, how does international law actually regulate them? Well, it all comes down to this one single unifying metric, 2.8 bar. It is a non-negotiable law of physics that has been translated straight into legal code.
Under the IGC Code, if a liquid's vapor pressure at a standard tropical temperature of 37.8 degrees Celsius exceeds 2.8 bar absolute, standard tank structures will literally fail. You are legally required to use a purpose-built gas carrier. To put that into perspective, propane hits roughly 13 bar at that exact same temperature. This is exactly why substituting cargoes blindly is so incredibly deadly, and why actual vapor pressure verification before loading is a mandatory survival check, not just some administrative formality to keep the port agent happy.
Ultimately, it all boils down to this. A misidentified cargo isn't an admin mistake. It's a fatal physics mismatch. Do you truly know what is flowing through your manifold? Because every single time those valves open, you are shaking hands with the raw laws of thermodynamics. Think about that the next time you look at a cargo manifest. I really hope this explainer has challenged some of your assumptions today, and we'll definitely see you in the next deep dive. Stay safe out there.